welcome all of you to David Warsinger's defense, and look forward to hearing what David has to say today. David actually comes to us from Cornell originally, where he did his bachelor's and master's degrees. He was top of his class in the master's program at Cornell, did very well in the undergraduate program also. Here at MIT, David has worked with us on membrane distillation since he arrived. He's been on a project jointly sponsored by the Masdar Institute, and Professor Hassan Arafat, who's connecting by video, is from Masdar and also a member of his committee. David here at MIT, among other things, has received the Outstanding Europe Graduate Mentor Award for his work with undergraduates. I believe, David, you supervised something like 12 Europs. Maybe not quite that many, but the numbers are certainly up there. He's been running a small army. David has also received honorable mention for the Water Night Best Poster Award. He's participated in a project at the Harvard Innovation Lab where they got a co-grand prize. And he's done a number of other things, gotten other awards before he came to MIT at Cornell. At MIT and through his work at Cornell, David has been first author on about 10 journal and conference papers, either published or in progress. He's also been a co-author on another 10 journal and conference papers. And he is an inventor or co-inventor on approximately 11 technology disclosures and or patent applications or issued patents. So with all of that said, I think you can see who you're about to listen to. And I will turn the floor over to you, Dave.
Thank you, Professor. Hi, everyone, and welcome to my doctoral defense. My research has been on the thermodynamic design and fouling of membrane distillation systems. I'm going to start with the world global water crisis. We see on this map all the regions where, in red, people are using up the entirety of the renewable water at the location, which is the sum of the rainwater that they receive annually. Globally, about 50% of the world's population uses all the renewable water at their location. Now, unlike most socioeconomic trends, which are improving, water shortages are actually getting worse. Between the year 2000 and 2025, the amount of people experiencing water shortages is expected to increase by 4-fold. Lack of access to clean water also causes significant deaths from waterborne disease and pollution. Roughly 3 million people die per year from lack of access. This is only exceeded by heart disease, smoking, and hunger. Membrane distillation is one of the technologies that can help address this global water problem. Membrane distillation has several distinct advantages. It can be very efficient. It scales down to small sizes very well while maintaining good efficiencies. Also, it provides very good rejection of salt, over an order of magnitude better than that of the most common technology, reverse osmosis. And finally, it's very fouling resistant. The membranes being good at resisting fouling compared to other technologies like reverse osmosis, but prior to my work, this has been very poorly understood. Because of these advantages, many companies have taken interest in membrane distillation, mostly over the last 5 or 10 years. So what is membrane distillation? Very simply, it's a desalination technology that uses a hydrophobic membrane that allows water vapor to pass through, but not liquid water. A temperature difference across the membrane creates a vapor pressure difference, which drives vapor to diffuse through the hydrophobic membrane. Now, to implement these systems in the real world, we need a hot source and a cold source for these systems. So what's commonly done is a countercurrent heat exchanger-like setup, where feedwater enters, gets heated, and then goes back down through the system. This allows for recovering of the heat as it goes through the process, and thus providing very good efficiencies in a very simple fashion. Membrane distillation has a variety of different applications that have been both used and been identified as potential uses. Membrane distillation has been used in one of the original applications in the food and beverage industry, concentrating fruit juice, for instance. It has also been used for seawater desalination. And it's been proposed and used to treat frack water and thus reducing the water consumption of these fracking sites and helping combat the issue of these earthquakes we see as a result of fracking. It's also, because the water provides is so pure, been used in the pharmaceutical and semiconductor industries to create very pure water. It can be used in the textile industry to treat those waters, and it can also be used with waste heat to provide fairly low energy demand desalination. I divided my work into two parts on studying the efficiency and fouling membrane distillation, each having their own 3 parts. For the efficiency studies, I examined waste heat versus competitors, the effect of the tilt angle in membrane distillation, and an innovation using superhydrophobic condensation to increase the performance of air gap membrane distillation. For my fouling studies, I looked at the gaps in the literature. I did a study on nucleation and filtration to minimize fouling in the system, and provide an innovation of using protective air layers to reduce fouling in membrane distillation. So first, starting with waste heat. A common question that has not been answered is, how does membrane distillation perform compared to other technologies on waste heat? Waste heat from data centers or other sources can vary in the temperature provided. And in fact, there's been no study in the past that really compares different systems to one another to compare how they perform and how their components differ using different temperatures of waste heat. For a waste heat thermal desalination system, we can imagine a black box which has a heat input at some given top temperature of the waste heat, takes in seawater, and rejects out heat at a lower temperature, brine, and pure water. If we also want to compare this to electrically driven technologies, then we need a heat engine. The most feasible system for these sizes is a Rankine cycle, which can be paired to take the heat input and provide work to desalinate water. The first system was a multi-stage membrane distillation system modeled. Here is like membrane distillation I described before, but you have multiple stages, each at their own matched pressure and temperature. For the system, you have a top temperature at the heat input and recovery throughout the different stages. Thermodynamically, the system behaves a lot like multi-stage flash. But I'm not going to go into the details, but this is kind of the configuration. While under normal conditions, operating at normal hot top temperatures, the entropy generation, which represents the thermodynamic losses in the system, is dominantly in the heat exchangers and the membrane distillation modules itself in those stages I showed you on the last slide. However, once we start using lower temperatures, this picture changes a whole lot. The other heat exchangers, including the top heat exchanger and the brine regenerator, start becoming very significant in making up the losses from membrane distillation. This is largely due to the fact that the lower temperature gives you a reduced recovery, so the relative volume of the feed and brine streams is much larger compared to the condensate that you're producing. We find the same trend in the losses for temperature disequilibrium, which is losses because the water you reject to the environment is warmer than the surroundings. We modeled 6 other different technologies, including membrane distillation, including 3 very common representative thermal technologies and 2 leading electrically driven technologies. In these results, we found a similar trend. All the various thermal technologies had significantly decreased performance in the thermal components that had the feet and brine streams, but not so much in the actual stages themselves, indicating how one should try to innovate to improve these systems to operate off lower temperature waste heat. We found the same trend for losses due to mixing when the water is warmer than the surroundings. This paper was kind of like 6 in 1. A little tricky. Overall, we find that membrane distillation compares fairly favorable to the other thermal technologies, but is still outperformed by reverse osmosis. However, compared to traditional pairing with the power plant, the relative performance of the thermal technologies fares much better compared to that of the electrically driven technologies of reverse osmosis and mechanical vapor compression. Next, I'm going to discuss the effect of tilt angle in air gap membrane distillation. There are several different configurations that are the most efficient possible configurations for single-stage membrane distillation. I focused on air gap membrane distillation, which is the most efficient given large surface areas and also given very saline feed solutions, as my collaborative work has shown. And I had collaborative work also studying permeate gap membrane distillation. For these systems, we needed a computational cell to model the behavior of membrane distillation in a numerical model. We used the finite difference method to integrate across several hundred computational cells, which each balanced heat and mass transfer. There's two equations I want to point out that are key to the performance of membrane distillation. One is the general flux equation. Essentially, the rate of the vapor going across the membrane is a function of a constant times the vapor pressure difference across the membrane. And finally, the film thickness of the laminar film condensation is a function of g cosine theta and the film thickness cubed. If the film thickness increases, then we can have a reduced air gap and can significantly affect the performance of the system. The air gap itself is the dominant source of heat transfer resistance and mass transfer resistance for the process. There are also some other elements modeled, such as boundary layer effects. There's several reasons why we want to better understand the performance of air gap membrane distillation at varying tilt angle. For one, it's one of the most common configurations, and despite this, in the literature, systems have had a mix of vertical and horizontal setups with really no method to figure out which one they should actually be using. Second, membrane distillation has been suggested to be paired with solar thermal power, and in fact, a previous PhD thesis from our lab by Edward Summers used solar thermal power to power air gap membrane distillation. If you want to maximize solar insolation, you may want to optimize a tilt angle for your given latitude. And so you very well might want a tilted system. Finally, systems of different configurations, besides flat plate, which is the most common, such as a spiral wound module or a conical module, can have different angles in the way they're set up. So it's important to understand how this angle affects overall system performance. So this is a description of the experimental apparatus. We have the membrane distillation setup I showed you previously. And we have paired a hot reservoir and a cold reservoir to maintain known temperatures across both sides of the system. We also have a variety of pressure, temperature, and mass flow rate sensors and various controls in the system. This is what this actually looks like in practice. To tilt the module, we have an axis here where this module tilts back and forth in either direction. To define this work, I'm going to indicate negative or declined angles tilting this way as angles where the condensate plate is above the membrane itself. And I'm going to describe positive or inclined angles when the membrane is above the condenser plate, which is more common than this configuration. Overall, we found that in the modeling results, we expected a very small difference in the overall performance of membrane distillation based off of tilt angle. This is due to the relationship between cosine theta to the 1/3 and the film thickness. So not until you get to extreme angles does the film thickness appreciably change. However, at declined angles, we start seeing the permeate flow rate increase. What's happening is we have this thermal bridging where water falls from the condensate plate onto the membrane and drains out the system that way. That reduces the resistance and starts making the system behave a little bit like a flooded system, which is what we saw at really extreme angles, where the gap entirely flooded because there wasn't sufficient angle to drain the system. This behaves much like the permeate gap system I mentioned at the beginning of this presentation. So overall, we found that we can really tilt these systems quite a bit without any effect on performance, which is very promising for applications to solar thermal membrane distillation. And we also found two different scenarios that can happen when we tilt it in extreme angles. My next work studying membrane distillation efficiency was an innovation. This was to use superhydrophobic condensation to improve the performance of air gap membrane distillation. In traditional film-wise condensation, we have this air gap, which provides the dominant heat transfer and mass transfer resistance to the system. the heat transfer resistance is favorable. We don't want any heat transfer between the hot and cold side that isn't used to produce more condensate. However, by providing a mass transfer resistance by slowing diffusion, it slows the overall permeate rate, thus requiring us to need more surface area to achieve the same performance. Now, we can use these superhydrophobic surfaces which have a droplet or jumping droplet condensation instead of a laminar film. In these systems, we have these droplets that they combine, and these are very small droplets, around 100 microns, and when they combine, the surface area decreases. The energy is dissipated into kinetic energy, so they wobble, and the surfaces are so hydrophobic that they eject off the surface, as we see here. This reduces the overall diffusion resistance by having better mixing in the gap and additional condensation on the droplets themselves as they fall out of the system. It also avoids the temperature gradients that are unfavorable, such as that along the laminar film itself. To create such surfaces, we had coating help from the DRL group. This coating provides really nice, very rough surfaces, providing a very high roughness and thus getting good Cassidy-Baxter behavior of these droplets. Using copper oxide makes it highly conductive, and it was then coated with a siliconized coating to chemically increase the contact angle. Here we see the surface before and after being coated. Overall, we found that in the superhydrophobic case, the overall permeate flux actually increased pretty substantially. We've modeled this against a water gap case which entirely lacks the mass transfer resistance of the air gap, and found that by introducing superhydrophobic condensation, we almost entirely remove the mass transfer resistance. Now, at higher driving temperatures, the performance of the control of laminar film condensation and the superhydrophobic surface converged. This is due to the fact that with our small air gap size and geometry, the system became flooded in both cases and so performed similarly. However, in real systems, we have a much smaller temperature difference between the two sides, indicating that we'd be more in this range where performance is enhanced by as much as 116%. Given that air gap membrane distillation can thermodynamically be the most efficient of the membrane distillation configurations, this is a substantial way to improve the overall performance of membrane distillation. This work is under review by the Journal of Membrane Science, and a patent was submitted this last fall with collaborators in this room. So next, I'm going to discuss fouling in membrane distillation. First, starting with gaps in the literature. There are 4 types of fouling that can occur in membrane distillation. There is inorganic fouling, which is fouling of salts on the membrane surface. There's also particulate fouling, where small particles deposit on the membrane surface. Biofouling can be a variety of different things. It can be bacteria growing on the membrane surface. It can be fungi. It can be a biofilm produced by either. It can be other organic compounds. And even it can also be small microorganisms, such as seen in some seawater systems. Finally, we have membrane degradation, or damage to the membrane itself, such as cracking, that can occur during intermittent operation or using abrasive chemicals. This work was published in a review paper with other collaborators at NASDAQ. Overall, we've had a variety of effective mitigation methods for fouling in membrane distillation. However, there were some that were noticeable, and some of the most effective were not well understood. Using filtration to remove particles from the bulk was extremely effective in reducing the effects of fouling. However, it wasn't very well explained as to why that was. Membrane superhydrophobicity was more of a mystery. In studies that were coated with superhydrophobic coatings, fouling almost completely disappeared. In some cases, it actually baffled the authors. In one instance, they thought they must have made a mistake in their experiment because it was so hard to make fouling occur once they had a superhydrophobic coating. Some of the other methods, such as high temperatures kill bacteria and using basic and acid washing to play with the saturation index, are fairly well understood. This work in filtration made me wonder, is nucleation happening largely in the bulk of the solution, and thus fouling is occurring as a result of bulk effects, not the membrane surface itself, which is conventionally thought and more thought of for other membrane processes? Does it dominate in the bulk rather than on the membrane surface itself? So let me give some background. Nucleation is the process where particles in solution combine and grow to a significant size and eventually precipitate, or not necessarily precipitate, but adhere to a surface outside the system. There are several types of nucleation. Primary nucleation occurs in systems where there is primary nucleation occurs in the absence of crystals in the bulk. There are two types of primary nucleation. There's homogeneous nucleation, which occurs in a pure solution. This is actually very hard to make occur in practice and would take very pure solutions. In reality, to really make this happen, and you need to do an experiment with levitation, such as on the space station. In most real systems, you have heterogeneous nucleation, which is induced by foreign particles and surfaces, such as atmospheric dust or other contaminants in the system. This is the most common form in most membrane distillation systems. There's also secondary nucleation, where crystals that have already formed break off into different pieces, and then these pieces start to grow rapidly. In a membrane distillation system, you do not want this at all, and this one can occur even at very low saturation indices. Meanwhile, for heterogeneous and homogeneous nucleation, you can go to fairly high saturation indices, which is a measure of how far you are above the saturation level for that salt before you see significant fouling occur. So let's take a look at the thermodynamics for this process, for nucleation. There's an energy barrier for nucleation that is maximum at a critical radius size. What's essentially going on is you have these competing terms. At very small sizes, you have very high surface area relative to the volume. The surface tension, which is an area effect term, is acting against you forming these nuclei. But a volumetric term, which is a function of essentially chemical potential, wants these salts to precipitate. So through essentially statistical random action, eventually enough of the particles combine to form a critical stable nucleus. Once it reaches the size, instead of redissolving into the bulk, it starts to rapidly grow as a crystal. If you can stay on this side of the equation for long enough, you can mostly avoid fouling and run at supersaturated conditions. There's been a fundamental theory called classical nucleation theory, linking the Gibbs free energy barrier to a function of the different surface tensions between the salt, the solution, and the substrate you're working with. Critically, the induction time is an exponential function of this Gibbs free energy barrier. So small changes in the Gibbs free energy barrier will cause dramatic increases in the amount of fouling that occur. I had the idea of linking this theory with Young's equation using the contact angle that's traditionally used to measure superhydrophobicity, which includes the vapor, liquid, and solid, and not the crystal. This way we can use the easily measured contact angle that describes membrane hydrophobicity and see the effect on the fundamental nucleation on the membrane surface. In finding these numbers, I found that when coating my PVDF membranes and using values for gypsum, PVDF, and water, the Gibbs free energy barrier multiplies dramatically by a factor of 33 as the contact angle increases from what we traditionally measured in our solution, 125 degrees, to our coated angles in the superhydrophobic study I will get to shortly. So in short, we have an explanation for what we found in the literature, that superhydrophobic contact angles can reduce fouling, tying into nucleation and the induction time. Long story short, superhydrophobic membranes we can expect from theory as well as previous practice to reduce overall fouling. To test the ideas of the dominance of bulk nucleation, we took the membrane test bed, which I mentioned previously, and simply added a filter into the system. To really test if bulk nucleation was dominant in membrane distillation, we're going to make conditions very unfavorable to bulk nucleation and see if bulk nucleation still dominated fouling by removing a good portion of the bulk nucleation with this filter. So we used a uncoated PVDF membrane, so it wasn't too hydrophobic. We used a higher concentration near the membrane itself by dramatically reducing the flow rate of the system, and thus encouraging more nucleation on the membrane surface. We used a really pure system through using DI water and thorough cleaning protocol to minimize any nuclei for heterogeneous nucleation in the bulk. We minimized any metal parts or other parts that could encourage nucleation on other surfaces. And we used calcium sulfate, a salt that's not too strongly affected by temperature, and also really minimized temperature gradients in the system for some other design innovations. We found that in the saturated case, with very high saturation and without any filter, there was really bad fouling. So the flux of the permeate dropped precipitously, and then the bulk was actually, the condensate was actually contaminated, and the conductivity or salinity of the condensate increased dramatically. And in fact, it increased so much that the actual overall flux increased as well, indicating very bad fouling and a total loss of a really productive membrane distillation process. In looking at these membranes via SEM, we find that the crystals tend to be very localized. Most of the membrane surface remains as is, as just a polymer, but the small crystals grow dramatically. My prediction with particulate fouling is that small particles that are already growing deposit on the membrane surface and then grow. And if you can remove that process, you can dramatically decrease fouling in membrane distillation. Our overall results showed that the introduction of a filter to remove a significant fraction of the bulk nucleation dramatically decreased fouling in membrane distillation. In fact, even in the case where we had extreme fouling and total destruction of the process, in a case where the filter was applied, we had some flux decline from blocking of the membrane pores, but we had no leaking even after running the experiment for several days. So overall, we find that even in conditions very adverse to bulk nucleation is dominating fouling in membrane distillation. This work is going to appear in the IDA conference, and will be continued in another journal paper as well. This helps solve a lot of the mystery as to how to prevent fouling in membrane distillation, and why it has proven to be more fouling resistant than other technologies. And it also ties in with the whole contact angle, meaning that in the bulk, some of these particles are more favorable for nucleation, whereas the surface is not. Finally, I'm going to discuss innovation using protective air layers to reduce fouling in membrane distillation. Essentially, can you have an air layer on the membrane surface acting to block these particles from depositing on the membrane itself, and thus reduce overall fouling in membrane distillation? To do this, we had our PVDF membranes coated with PFDA by Amelia, who's here right now. And we did other tests to verify we didn't significantly impair the process, such as checking that the permeability did not change significantly. In the superhydrophobic case, you can actually see this visible air layer, where we have this weird sheen of air on the membrane surface. However, on the regular hydrophobic case, it just looked like any surface, like a piece of paper put under water. And this work is in a conference paper, a journal paper, and a patent. To do these studies, we used a beaker setup to have an empty membrane distillation membrane on top of a solution with a foulant. We used mixing of the water and the air to provide good heat transfer through the system. And we tried several different ways of introducing air layers into the system, including lifting the membrane up entirely and also adding saturated bubbles of air into the system. On the membrane itself, we see these sporadic crystals on the membrane surface. But when looking very close, we find that these crystals tend not to penetrate very, very deep into the membrane when the air layers are present, indicating that they may be able to help reduce some of the more exacerbating effects of fouling in membrane distillation. The wetting I showed you previously largely occurs when these crystals occur in the membrane pores, and thus allow for wetting through the membrane. But we see the crystals are very, very much on the surface here instead. Overall, we found that for alginate, which is a biological foulant, there was a really significantly reduced amount of fouling, in the order of 95 to 97% reduction of mass adhered to the membrane itself. Alginate is commonly produced by algae and is known to be an important foulant in that it occurs in the gel layer in seawater applications. For salts, we had positive effects from both having the air layers and the superhydrophobicity, but they were somewhat mixed as compared to the very obvious case of a huge improvement for biological fouling. Now, what's very promising about this is that while membrane distillation in the literature is known to be very resistant to scaling of salts, it is proven less resistant, or the opposite, worse, dealing with biological fouling. So we could potentially use the introduction of air layers to reduce biological fouling problems and give membrane distillation the best of both worlds. The effects for the salts were mixed, but this can be largely assigned to nucleation in the bulk. These bubbles, as they go through the system, or the other methods that they're being introduced, can actually cause nucleation. And many studies in the literature have seen nucleation of salt crystals around water bubbles. So controlling the process of the air-water interface and any heterogeneous fouling that can occur in that layer can be used to reduce this process as well, and thus allowing this to be a bit more effective on fouling of salts. To publish this, to share this work with you today, we had to submit the patent last night, and that was a bit of a fun little challenge. And due to a lot of lack of work in the literature, we actually applied this to other surfaces, not just membrane distillation, using air layers and maintaining them on a variety of surfaces to reduce fouling. So this comprises the overall work for my PhD thesis. There was a study on waste heat and comparing the effects of the performance of different components in membrane distillation, and comparing the technologies to one another using shared assumptions to see how they fared on different waste heat temperature sources. A study on the tilt angle of air gap membrane distillation found that while vertical angles were ideal if you really wanted to have an air gap membrane distillation, tilting did not have a significant effect, leading one to believe that for solar thermal systems they could still tilt systems freely without a worry of performance, and that many of the results on horizontal setups in the literature are still applicable, even though the film thickness might have varied a little bit. A review paper on fouling identified several key issues in the literature and several gaps that further work helped fill. A study on the effect of nucleation and filtration in fouling showed that in membrane distillation, fouling is mostly occurring in the heterogeneous form in the bulk. And if you make conditions limit heterogeneous bulk nucleation, you can significantly reduce the fouling in membrane distillation. And that's kind of also explaining past papers showing why membrane distillation is resistant to fouling. And this can be tied in to the thermodynamics of nucleation on these surfaces. And finally, I had a contribution on using an introduction of air layers to reduce fouling in membrane distillation. In addition to that work, I had a variety of non-first author papers, also contributing to membrane distillation, thermodynamic design, and fouling. This included work on the effect of the surface tension and how it changes in high salinity with membrane distillation, multi-stage vacuum membrane distillation, including a paper by Hyun Won that used the work I showed you at the beginning, using a conductive gap to have an improved permeate gap membrane distillation, which is also the work on, I think now about 3 patents, which Jay has been the lead on. Comparing different module configurations and their performance in memory distillation, work on multi-effect memory distillation, using seawater and the temperature difference between the deep ocean depths and the surface to drive memory distillation or other desalination technologies, studying different fouls and how they affect wetting with memory distillation, and in situ visualization of fouling in memory distillation. And finally, the creation of memory distillation membranes and testing their performance with Amelia. So with that, I wanted to briefly show the publications. The first author, collaborative author, as well as patents I've worked on for my work and other work, and presentations that are academic in nature. Finally, I'd like to thank the Masdar Institute for their support and for funding my PhD, MIT itself, the Technology Licensing Office for handling our patents, and our really wonderful lab group who provided excellent feedback at every group meeting and really helped improve this work. I also wanted to thank my wonderful fiancée, Andrea, with the most embarrassing picture I could find.